Event horizon is a kind of threshold that separates the black hole from the outside world. The nature of black holes is studied thanks to Albert Einstein's general theory of relativity. The theory predicts that the mass of the black hole warps spacetime, forming a gravitational well. This deformation is so strong that it affects the trajectories of light and matter. For example, light passing near a black hole can be warped, forming an effect known as gravitational lensing. There are several types of black holes depending on their mass. Stellar black holes are formed by the collapse of massive stars and have a mass that is usually 3 to 10 times the mass of the Sun. Supermassive black holes are found at the centers of galaxies, including our own Milky Way. Their mass reaches millions or even billions of solar masses. Their origin remains a mystery, but they are thought to form due to the merger of smaller black holes and the absorption of matter over billions of years. Another category is intermediate black holes, which have masses ranging from a few hundred to several thousand solar masses. Their presence has only recently been confirmed thanks to modern observational methods, such as gravitational wave astronomy. The phenomenon of Hawking radiation adds another mystery to the nature of black holes. Stephen Hawking predicted that black holes are not completely black, they can lose mass and energy due to quantum effects, emitting weak thermal radiation. This phenomenon is explained by the interaction of particles and antiparticles at the event horizon. A single particle can fall into a black hole and the other escapes, causing the black hole to gradually evaporate. Space traps are also a place of extreme phenomena. If we imagine that an object falls into a black hole, it undergoes a phenomenon known as spaghettization. This is due to the difference in gravitational forces between the near and far sides of the object. Gravity is so strong that the object stretches into a long and thin thread. The study of black holes is carried out using various methods. For example, telescopes capture the X-ray radiation that is produced when gas and dust are heated to extreme temperatures before falling into a black hole. Gravitational waves are also used, fluctuations in spacetime caused by collisions of black holes. In 2015, for the first time, such waves were recorded, which was a revolutionary discovery in physics. These objects can interact with other objects in the universe. For example, they are able to absorb stars that pass too close, forming powerful accretion disks of matter orbiting the event horizon. In such cases, there is an emission of relativistic jets, jets that spread over thousands of light years. However, these cosmic craters are not only destructive. They may also play a key role in galaxy formation. Supermassive dark zones in the centers of galaxies regulate the processes of star formation, influencing the distribution and movement of matter. This relationship between black holes and galaxies is one of the most pressing topics in modern astrophysics. Gravitational collapse objects are also important for studying the fundamental laws of nature. They are laboratories for testing relativity, quantum mechanics, and their interactions. For example, the problem with the information paradox is that quantum mechanics requires the conservation of information, while general relativity assumes its annihilation in a singularity. This question remains unresolved and is one of the key mysteries of physics. The phenomena of space and time capture the imagination of not only scientists, but also a wide audience. They inspire science fiction, where they are often depicted as gateways to other dimensions or time machines. And although these concepts are hypothetical, they stimulate interest in the study of the universe. In 2019, the world saw for the first time a photograph of a black hole taken by the Event Horizon Telescope. This image was a confirmation of the theory of relativity and demonstrated the power of modern technology. Dark gravitational forces remain one of the most intriguing objects in space. Studying them opens up new horizons for science, helping us better understand the nature of the universe and our place in it. An incredible source of inspiration and research, so it is worth delving even further into aspects of their impact on space, physics, and our understanding of reality. One of the most interesting topics in the study of black holes is their effect on the surrounding matter and radiation. When material, such as gas, dust, or even a star, falls into the gravitational field of a black hole, it does not immediately disappear into the singularity. Instead, matter forms an accretion disk, a structure that consists of heated gas orbiting a black hole. Due to friction and gravitational forces, the gas in this disk heats up to millions of degrees, emitting energy in the X-ray spectrum. It is this radiation that makes black holes visible to astronomers, because they themselves do not emit light. Supermassive black holes, which are located at the centers of galaxies, are often accompanied by powerful jets of high-energy particles escaping from poles of the accretion disk. These jets can reach thousands of light-years and significantly affect the galaxy's environment. For example, they are able to expel gas from the galaxy, slowing down or even stopping the process of star formation. Such interactions are an example of how black holes can influence the evolution of galaxies and the formation of cosmic structures. In addition, they can merge with each other, forming even more massive objects. The merger of these astronomical objects is accompanied by the emission of gravitational waves, which were predicted by Einstein in his general theory of relativity. In 2015, it was possible to register these waves for the first time, and this discovery was revolutionary. It not only confirmed the theory, but also opened a new era in astronomy, the era of gravitational wave observation. Another intriguing topic related to these objects is their formation and growth. Although the process of stellar black hole formation is more or less clear, the origin of supermassive black holes remains a mystery. How did they reach such huge masses in a relatively short time after the Big Bang? There are several theories. One of them suggests that supermassive black holes form from seeds, primordial black holes that appeared in the early universe. Another hypothesis suggests that they grow by absorbing large volumes of matter or merging with other subjects of the astrophysical singularity. Even more exotic is the idea of primordial black holes, which could have arisen shortly after the Big Bang due to fluctuations in the density of matter. Such objects could have a variety of masses, including very small ones. If they exist, primordial black holes could explain some mysterious phenomena, such as the nature of dark matter, which makes up a large part of the mass of the universe but still remains elusive. The existence of these gravitational monsters poses numerous philosophical and theoretical questions to science. For example, is it possible to travel through a black hole? Theorists suggest that a black hole could be a portal to another universe, or even to another time. These ideas remain speculative, but they stimulate scientific research in the field of quantum gravity and the nature of space-time. The paradox of information in black holes is another unsolved problem in physics. If an object falls into these space traps, all information about its properties seems to be lost when it reaches the singularity. However, quantum mechanics states that information cannot be destroyed. This contradiction has become one of the central questions in modern physics, and solving this puzzle could lead to a revolution in our understanding of quantum mechanics and gravity. Another mystery is the nature of the singularity, which is the central point of a black hole. In a singularity, the laws of physics that we know cease to apply. It is a place of infinite density and curvature of spacetime. Current theories such as quantum gravity and string theory try to explain exactly what happens in a singularity, but there is no definitive answer yet. These light absorbers also have a huge impact on popular culture. They are often depicted in movies, books, and video games as mysterious, dangerous objects, or as means of traveling through time and space. For example, in the movie Interstellar, the gargantua black hole became the centerpiece of the plot, and her image was created using real scientific models, making her one of the most accurate in cinema. In conclusion, black holes are not just mysterious objects that challenge our understanding of the universe. They are the gateway to new knowledge and understanding of how our space works. Studying them is not only a journey into the world of extreme phenomena, but also the key to unraveling the fundamental laws of nature that underlie everything that exists. Black holes remain the focus of attention of astrophysicists and theorists alike, because they open up limitless horizons for scientific research and reflection on the nature of reality. To further understand their essence, it is worth considering additional aspects, such as their connection to dark energy, quantum effects, as well as their role in the large-scale structure of the universe. One of the most exciting theories is the suggestion that black holes may be related to dark energy, a mysterious force that accelerates the expansion of the universe. Some current models put forward the idea that the vacuum energy that surrounds black holes could be a source of dark energy. If this is true, then these gravitational wells play a much larger role in cosmology than we can imagine. It also opens up opportunities for new approaches to solving one of the main mysteries of modern science: why is the universe expanding at an ever faster rate? The quantum aspects of black holes are one of the most active research topics. As mentioned, Stephen Hawking predicted that black holes emit energy through a process known as Hawking radiation. This process demonstrates the interaction of gravity with quantum fields and suggests that black holes can gradually lose mass and eventually evaporate. This phenomenon highlights the relationship between quantum mechanics and general relativity, but also reveals a deep contradiction between the two. These contradictions, known as the information paradox of black holes, stimulated the development of new theories, such as the holographic principle. This principle states that all the information that falls into a black hole is stored on its event horizon in the form of a quantum code. If true, then black holes could act as a kind of storage devices for information about the universe, which opens up exciting prospects for quantum physics. Objects with critical gravity not only destroy, but also create. They play an important role in the formation of galaxies and large-scale structures of the universe. For example, supermassive black holes can act as architects, forming galaxies through their gravitational interaction. Their ability to influence the movement of gas and dust around them creates conditions for star formation. In some cases, however, supermassive black holes can slow down this process if their jets cleanse the galaxy of the gas needed to give birth to stars. One of the most striking phenomena associated with black holes is relativistic jets, or jets. These jets are formed by extreme magnetic fields that are generated by accretion disks around rapidly rotating black holes. Jets contain charged particles that are ejected at speeds close to the speed of light. They are able to penetrate intergalactic space, affecting nearby galaxies and even creating shock waves in intergalactic gas. The study of jets helps scientists better understand not only the nature of black holes, but also the evolution of galaxies and quasars, extremely bright objects that gain energy from the accretion of matter onto supermassive black holes. And while black holes are often associated with destruction, they also open the door to ideas about traveling through space and time. In general relativity, the existence of so-called wormholes is allowed, hypothetical tunnels that can connect different points in spacetime. Although the existence of wormholes has not yet been confirmed, their study offers hope for the development of future interstellar technologies. Gravitational influence zones are ideal objects for testing new theories. They challenge our knowledge of high-energy physics, quantum fields, and gravity. Future research with advanced telescopes such as the Space Telescope James Webb, as well as new gravitational wave detectors, will allow you to penetrate even deeper into their nature. Black holes are not just dark spots on the map of the universe. They are the key to nature's deepest mysteries, from the beginning of time to the limits of space. Studying them not only expands our knowledge of the cosmos, but also raises fundamental questions about what it means to be part of this boundless and mysterious universe. One of the most interesting concepts is the idea that black holes can be energy sources capable of fueling the evolution of galaxies and even creating entire cosmic structures. The enormous amount of energy released during the accretion of matter exceeds the energy produced by stars, and this energy is capable of influencing the chemical composition and dynamics of gas in galaxies. This phenomenon, known as active galactic nucleus feedback, can stop star formation or change the ways in which new galaxies form. Quasars, one of the brightest objects in the universe, are an example of such processes. They are powered by the energy released during the accretion of matter onto supermassive black holes, and their brightness can surpass the glow of all the stars in the galaxy combined. Observations of quasars allow scientists to study the conditions that prevailed in the universe in the early stages of its evolution. Dark matter is another mysterious substance that makes up about 27% of the mass energy of the universe, but does not emit light, so it cannot be observed directly. Black holes are often seen as candidates for the role of reservoirs for dark matter. Although research has not yet provided definitive answers, there are theories that black holes can interact with dark matter particles, creating unique gravitational signatures. For example, if primordial black holes formed in large numbers in the early universe, they could be major components of dark matter. However, this idea remains speculative, since no clear evidence of the existence of such objects has yet been found. Observations of black holes that existed several 100 million years after the Big Bang raise questions about their origins. How were they able to reach such masses in such a short time? One possible answer is the direct collapse hypothesis. In this scenario, large clouds of gas could collapse directly into the black hole, avoiding the star formation stage. Another option is accelerated growth due to the efficient absorption of matter. The study of early black holes allows scientists to better understand the conditions that prevailed in the young universe, including the formation of the first galaxies and stars. Imagine two black holes orbiting each other, gradually getting closer. This process is accompanied by powerful gravitational waves, fluctuations in spacetime that propagate at the speed of light. When two black holes merge, they emit huge amounts of energy in the form of gravitational waves. The first such waves were recorded in 2015 by the LIGO Observatory, which was a revolution in physics. These events not only confirmed the existence of black holes and mergers between them, but also opened up a new way of studying the cosmos. Gravitational waves allow us to hear the universe, allowing us to study objects and phenomena that are inaccessible to conventional telescopes. One of the biggest challenges of modern physics is the unification of two fundamental theories, quantum mechanics and general relativity. Black holes are at the junction of these two sciences, which makes them ideal laboratories for developing new theories such as quantum gravity. For example, the question of whether information that falls into a black hole is stored remains a central problem in physics. If this problem is solved, we can get the key to a theory of everything that will unite all the fundamental interactions of nature. Even though black holes are associated with the end, they can also be the key to the future. There are ideas that the use of energy released during the accretion of matter can provide humanity with an almost infinite source of energy. Such ideas remain fantastic, but they highlight the importance of black holes in understanding not only the cosmos, but also our potential as a species. Compact massive objects continue to capture the imagination and raise questions. Not only are they objects of extreme physical phenomena, but they also make us think about deeper questions of being, such as the nature of reality, time and space. Studying them is a journey that never stops and leads us to discover new facets of the universe. Black holes are objects that never cease to amaze and delight with their mystery. They are the result of an extreme fusion of space and time, where the laws of physics that we know cease to operate in the usual sense. Their appearance requires the fulfillment of strict conditions, but this is what makes them so interesting to explore. A star that has exhausted its nuclear fuel survives a collapse to form an ultradense object with gravity capable of holding even light. This process occurs with the participation of gravity, which begins to prevail over all other forces, causing the matter of the star to contract to extremely small sizes. The result is a singularity, where the density and curvature of space become infinite. An event horizon forms around the singularity, a boundary beyond which even light cannot escape. This makes black holes invisible, but they leave traces in the space around them. Scientists learn about their existence due to the effect on nearby matter or radiation that occurs due to the heating of gas in an accretion disk. The temperature in such disks can reach millions of degrees, generating X-rays that can be recorded with modern telescopes. The study of black holes opens up the opportunity for us to look into the depths of space and time, because they have been formed over billions of years. One of the biggest discoveries in the study of these objects was the observation of gravitational waves caused by the collision of two black holes. These waves not only confirmed the predictions of general relativity, but also made it possible to look at the dynamics of the universe. Black hole mergers are events of colossal proportions in which energy equivalent to several solar masses is released. Some cosmic vortices reach masses that are millions or even billions of times the mass of the Sun. Such objects are called supermassive black holes. They are found at the centers of galaxies and are believed to play a key role in their formation and evolution. For example, our galaxy, the Milky Way, has a supermassive black hole called Sagittarius A** at its center, which is 4 million times the mass of the Sun. It influences the movement of stars and gas in its vicinity, forming the characteristic structure of the galaxy. The nature of dark gravitational forces remains the subject of numerous theoretical debates. For example, The Hawking radiation predicted by Stephen Hawking suggests that black holes can evaporate due to quantum processes at the event horizon. This discovery challenges our understanding of gravity and quantum mechanics, which seem to contradict each other under these extreme conditions. The theory suggests that a particle-antiparticle pair can occur near the event horizon. One of them can fall into a black hole and the other can escape, resulting in a loss of mass in the black hole. Another important topic is the information paradox of black holes. According to quantum mechanics, information about the state of any system must be stored, but general relativity predicts that all information that falls into a black hole disappears in a singularity. This contradiction has been the catalyst for the development of new theories, such as the holographic principle, which states that information is stored on the surface of the event horizon in the form of a two-dimensional holographic code. Black holes are also laboratories for testing the wildest hypotheses. For example, the idea that black holes can be gateways to other universes or even wormholes that allow travel through space and time. Although these concepts remain speculative, they open up new horizons for reflection on the nature of the universe. The abysses of space and time force us to rethink the fundamental laws of nature and expand the boundaries of our understanding of reality. Studying them not only allows us to look into the deepest corners of space, but can also lead us to revolutionary discoveries in physics that will change the way we see the universe. This is an endless journey that opens up new mysteries and challenges for us. Light absorbers are not only objects that challenge our understanding of physics, but also a source of inspiration for new discoveries. They appear on different scales, from stellar to supermassive, and their impact on the universe is enormous. Black holes can be the driving force of the evolution of galaxies, to influence the distribution of matter and energy in intergalactic space, as well as to suggest how the first structures in the universe were born. The merger of these stellar tombs was one of the most spectacular phenomena astronomers have observed. As two black holes orbit each other, they emit gravitational waves that gradually take away the energy of the system, causing the black holes to move closer to each other. Eventually, they merge to form a new black hole that may have a mass greater than that of both original objects. This process is accompanied by the release of an enormous amount of energy, equivalent to several solar masses, in the form of gravitational waves. These waves were first recorded in 2015 by the LIGO Observatory. This discovery not only confirmed the existence of black holes and gravitational waves predicted by Einstein, but also became the first direct evidence of the existence of a system of two black holes merging. Since then, dozens of similar events have been recorded, allowing scientists to study the properties of these exotic objects, as well as their role in the formation of the universe. Supermassive black holes at the centers of galaxies are the largest of the known types. Their masses reach billions of solar masses, and they have an enormous impact on the galaxies in which they reside. For example, the black hole at the center of the Milky Way, Sagittarius A*, is surrounded by clouds of gas and dust, as well as stars that orbit it at extraordinary speeds. Observation of these stars allowed scientists to accurately determine the mass of the black hole and its location. Some supermassive black holes create accretion disks from matter falling into them. These disks heat up to such temperatures that they begin to emit energy in the form of light and X-rays. This is how quasars appear, one of the brightest objects in the universe. The light we observe from quasars may be the result of events that occurred billions of years ago, making them a kind of lantern of the past. The existence of black holes also raises fundamental questions about the nature of time and space. The theory of relativity shows that the gravity of a black hole is so strong that time near it slows down. This phenomenon, known as gravitational time dilation, was demonstrated in the movie Interstellar, where characters experienced different time speeds due to the influence of a black hole. Even more exotic are the assumptions that black holes can be wormholes, tunnels that connect different points in space-time. Although this is still a hypothesis, such ideas make us think about the fact that black holes can be not only destroyers, but also pathways to new dimensions. Current research on black holes focuses on the combination of quantum mechanics and relativity, which is key to understanding what they are. Hawking radiation, for example, shows that black holes can gradually lose their mass and eventually disappear. This contradicts the idea of their absolute darkness, and indicates that even the most powerful objects obey the laws of quantum physics. Dark zones are mysteries that force us to rethink the limits of our knowledge and constantly ask new questions. They open the door for us to understand the deepest processes in the universe and, perhaps, one day will help us find answers to questions about the beginning of time, the nature of space and our role in this boundless cosmos. Black holes continue to amaze with their mysterious properties, and every aspect of their existence gives rise to new theories, hypotheses, and discoveries. One of the most interesting topics is their potential impact on the global evolution of the universe, as they may be related to many of the fundamental processes that shape the cosmos. Let's imagine the early universe, a few 100 million years after the Big Bang. The first stars to form were extremely massive and quickly exhausted their fuel. When such stars exploded as supernovae, their cores collapsed, creating the first black holes. These black holes may have become the building blocks for the supermassive black holes that are now located at the centers of galaxies. In the early universe, they could merge with each other, absorb matter, and gain mass rapidly. Black hole mergers may have played a key role in galaxy formation. The gravitational waves emitted during these mergers affect the distribution of matter in the universe, creating the large-scale structures we observe today. Supermassive black holes located at the centers of galaxies also control accretion processes, ejecting powerful jets that can clear galaxies of gas and affect the rate of star formation. The existence of supermassive black holes in the young universe is one of the great mysteries of modern astrophysics. How were these objects able to reach such huge masses in a relatively short time? One explanation is that the early universe may have had very favorable conditions for the rapid growth of black holes. For example, large gas clouds could directly collapse into black holes, bypassing the star formation stage. Another possibility is the extremely efficient accretion process, in which black holes absorbed huge volumes of matter. The cosmological role of black holes is not limited to their effects on galaxies. They can be related to the deepest aspects of fundamental physics. For example, there is speculation that black holes may have a connection with dark energy, which accelerates the expansion of the universe. Although these theories are hypothetical, they open up new avenues for exploring the relationship between gravity, quantum mechanics, and cosmology. Black holes also change our understanding of time and space. In the vicinity of a black hole, time slows down so much that, from the perspective of an outside observer, an object falling into a black hole appears frozen on the event horizon. This phenomenon is a consequence of extreme gravity, which warps the structure of space-time. In theory, Black holes can even serve as portals to other regions of the universe or alternate realities, although these ideas remain speculative. Modern technology allows us to study black holes with unprecedented precision. In 2019, humanity saw the shadow of a black hole for the first time thanks to the Event Horizon Telescope project. This achievement was a confirmation of the predictions of general relativity and showed how far our technology has advanced. In the future, similar projects, together with gravitational wave observatories such as LIGO and Virgo, will allow for even deeper study of these objects. Despite all the advances, black holes remain a mystery that provokes new questions. What happens inside the event horizon? How to combine quantum mechanics and gravity into a single theory that will explain their behavior? Is it ever possible to use black holes for interstellar travel? The answers to these questions can not only change our idea of black holes, but also help unlock the deeper mysteries of the universe. Black holes are objects that force us to push the boundaries of understanding, go beyond ordinary thinking, and look for new ways to explore space. They are the gateway to the deepest questions of science, and their study will undoubtedly continue for many centuries to come, opening up new horizons for us. These extreme masses remain some of the most mysterious and unexplained objects in the universe, and every aspect of their existence is full of mysteries. The deeper we dive into their nature, the more questions arise. Black holes force us to revise the fundamental laws of physics, opening up new horizons for research. One of the most intriguing aspects is the process of their formation and evolution. Stellar black holes form after the death of massive stars, when their cores collapse due to gravity. But how to explain the existence of supermassive black holes, the mass of which is millions or even billions of times the mass of the Sun? Their rapid growth in the early universe indicates that we do not yet understand all the mechanisms of their formation. Some theories suggest that they arise due to the direct collapse of giant gas clouds, others point to the possibility of absorption and merger with other black holes. Interestingly, there are assumptions about the existence of primordial black holes, objects that formed shortly after the Big Bang. Such black holes could have arisen due to fluctuations in the density of matter in the early universe, and their masses can range from very small to gigantic. If primordial black holes do exist, they could explain many mysteries, including the nature of dark matter. Dark matter remains one of the greatest mysteries of modern science, because it makes up a large part of the mass of the universe, but its nature is still unknown. Black holes also challenge our understanding of time. The theory of relativity shows that near a black hole, time behaves differently than under normal conditions. To an external observer, an object approaching the event horizon appears frozen in time. In the black hole itself, all the laws of physics cease to operate in the usual sense. This raises numerous theoretical questions, especially about what exactly happens in the singularity. A singularity is the point where the density of matter and the curvature of spacetime become infinite. General relativity cannot describe what happens under such conditions. This is where science needs new tools to describe reality, such as quantum gravity. Theorists, particularly string theorists, are working to create a model that could combine quantum mechanics and general relativity to explain the nature of the singularity. Space monsters also raise philosophical questions about the nature of information. According to quantum mechanics, information about the state of any system must be stored. But if an object falls into a black hole, that information appears to disappear into the singularity. This contradiction, known as the black hole information paradox, is one of the biggest problems in modern physics. Solving this paradox can help create a unified theory that unites all the fundamental forces of nature. Black holes not only cause theoretical controversy, but are also the objects of active observation. Telescopes such as the Event Horizon Telescope allow you to probe the event horizons of black holes and create their first images. These are incredible technological advances that demonstrate how far science has advanced. For example, a photograph of a black hole in the galaxy M87 showed not only the shadow of the event horizon, but also confirmed Einstein's predictions about the behavior of light in an extremely strong gravitational field. In addition, observations of gravitational waves from black hole collisions have ushered in a new era in astronomy. These waves are a kind of vibrations of space-time, and their study allows us to study the universe in a way previously inaccessible. They help detect black holes that cannot be seen by other methods and expand our understanding of their properties and distribution in space. Black holes also raise questions about potential interstellar travel. The idea that a black hole could be a gateway to another universe or to another part of our universe captures the imagination of not only scientists, but also science fiction writers. Although such concepts remain speculative, they stimulate interest in basic research. These objects not only reveal the mysteries of the universe, but also make us wonder about our own role in it. Black holes are a kind of windows to the extreme limits of reality, and their study expands our understanding of time, space, and existence itself. They are a challenge for science, but at the same time a source of inspiration that moves us forward towards new discoveries and a deeper understanding of the universe. Black holes are real space monsters that are both frightening and fascinating. Their nature is so amazing that at times it seems as if we are dealing with fantastic creatures, and not with objects of the real universe. However, they exist, and their impact on the surrounding space is so extensive that it can be felt even thousands of light-years away. Imagine a black hole lurking in the center of a galaxy. Its mass is millions of times greater than the mass of the Sun, and it, like the heart of a galaxy, affects all the processes around. The stars orbit it at breakneck speeds, as if dancing in a gravitational vortex. It is almost invisible, but its presence cannot be ignored. Matter approaching the event horizon begins to heat up to millions of degrees, emitting bright X-rays. It's like the death cry of a substance that is about to disappear forever. Even more stunning are supermassive black holes, which create huge jets of matter and energy escaping at speeds close to the speed of light. These jets reach thousands of light-years and are capable of affecting entire galaxies, changing their structure and dynamics. They give the impression that a black hole is a kind of engine that controls the evolution of space systems. However, even these phenomena seem simple compared to what can happen inside a black hole. What does a singularity hide? Is it really a point of infinite density? Maybe this is not the end, but the beginning of something completely different. Some scientists suggest that there may be other universes inside black holes, separated from our event horizon. Imagine that each black hole is a kind of eastern point to the new universe, which has its own laws of physics, time and space. Black holes also pose questions about the limits of reality. If we imagine that a person enters a black hole, his body is subjected to the phenomenon of spaghettization. This sounds almost ridiculous, but is actually the result of an extreme difference in gravitational forces between the near and far sides of the object. A person will stretch into a long, thin thread, turning into something completely unreal. But what's next? Will it disappear forever? Will it turn into energy? Or maybe leave some kind of trace in the very structure of the black hole? Equally intriguing is the idea that black holes may be the key to unraveling the nature of time. Time, as we understand it, behaves very differently near a black hole. Imagine that to an outside observer, an object falling into a black hole would freeze at the event horizon. But for the object itself, time will keep moving. How is this possible? This surprising behavior of time makes us wonder if a black hole could be some kind of natural mechanism for time travel. Now imagine that humanity will learn to use black holes in the future. For example, their gravitational energy can be a source of energy that surpasses all modern ideas about power. Black holes could serve as space engines that help ships travel between stars. Although it sounds fantastic, such ideas have been discussed many times within the framework of interdisciplinary research that combines astrophysics, engineering, and futurology. However, black holes are not only about energy and destruction. They are a kind of keepers of time and space. They show us that our universe is much more complex and amazing than we can imagine. Studying them is not just a science, but a journey to the deepest corners of reality, where we are faced with questions that touch on the very essence of being. Black holes are a symbol of infinity, the unknown and the unknown. They remind us that even in the world of science, where it seems that much is already known, there are always secrets worth exploring. It's not just about space, it's about ourselves, our ability to dream, explore, and seek answers to the most difficult questions the universe poses to us. Black holes continue to be a kind of gateway to the unknown, reminding us that even in the world of modern technology and enormous advances in science, there are limits that we have not yet overcome. They challenge our imagination, force us to rethink the basics of physics, and constantly open up new horizons for research. One of the most exciting ideas is that black holes could serve as sources of information about the early universe. Due to the fact that they are able to accumulate matter and absorb light, black holes become a kind of archives that store the history of the development of the cosmos. For example, observing supermassive black holes at the centers of distant galaxies allows scientists to get an idea of what the universe looked like billions of years ago. The light we see from these objects can travel to us for millions or even billions of years, revealing to us a picture of the distant past. Moreover, black holes help us understand the processes that occur on large scales in the universe. For example, when a black hole absorbs matter, it not only eats it, but also releases colossal amounts of energy in the form of radiation and jets. This radiation can accelerate the surrounding gas, creating huge cavities in intergalactic space. These cavities are part of the large-scale structure of the universe, which resembles a web, where galaxies and clusters of galaxies are connected by filaments of dark matter and gas. Dark zones also pose us with the question of whether there is a limit to knowledge. The singularity, which is at the center of the black hole, is where all the known laws of physics cease to apply. It is the zone where the density of matter becomes infinite and the curvature of spacetime reaches its limits. For it is almost unimaginable for us humans. We are used to ideas about causality, the clear passage of time and spaces that can be measured. But black holes indicate that there are regions of reality that do not yet lend themselves to our understanding. This is where the need arises to create a theory of everything, a model that would combine quantum mechanics and general relativity. Both of these theories are extremely successful in their fields, but when we try to apply them to black holes, they come into conflict. For example, quantum mechanics requires the preservation of information, but general relativity allows it to disappear in a singularity. This fundamental contradiction, known as the black hole information paradox, is one of the most important problems in modern physics. Another important aspect is Hawking radiation. The theory proposed by Stephen Hawking predicts that black holes are not completely black. Due to quantum effects at the event horizon, black holes can emit energy and even lose mass. Ultimately, this can lead to the complete evaporation of the black hole. But what is left after that? Will the information trapped in the black hole remain, or will it disappear forever? This question remains open. Gravity wells are also a source of inspiration for finding new ways to explore the cosmos. The gravitational waves that occur when black holes merge have opened up a whole new field of astronomy. These waves allow you to hear the universe, observe phenomena that cannot be seen with conventional telescopes. For example, the merger of two black holes can create a signal that allows you to determine their mass, distance, and even place in space. This is a new way of research that complements traditional methods and opens up new horizons for science. In the future, as technology becomes even more advanced, we will be able to look even deeper into the nature of black holes. For example, next-generation space telescopes will be able to study event horizons in detail and study processes that occur in the most extreme conditions. Perhaps one day we will even be able to create artificial black holes for research in the laboratory, which will help us better understand the fundamental laws of nature. Black holes are not only objects to study, but also philosophical symbols. They show us that even in the darkest corners of the universe, there is something worth exploring and discovering. They force us to expand the boundaries of our understanding and never stop in search of the truth. It's a reminder that science is a never-ending journey, and each new discovery only opens the way to even bigger questions. Objects with critical gravity remain in the spotlight as some of the most intriguing objects in the universe. They demonstrate that space is a place where the boundaries of our knowledge are blurred and opportunities are expanded. Their unique properties raise many questions that only stimulate our imagination and thirst for exploration. One of the most exciting topics is the interaction of black holes with their environment. Imagine a supermassive black hole at the center of a galaxy absorbing huge volumes of gas and dust. This creates a powerful accretion disk where matter rotates at incredible speeds, heating up to millions of degrees. The radiation that occurs in this process can be so strong that it can be seen from a distance of billions of light years. Such objects are called active galactic nuclei, and they are among the brightest light sources in the universe. Active galactic nuclei sometimes give rise to relativistic jets, narrow jets of high-energy particles that are ejected at speeds close to the speed of light. These jets can extend thousands or even millions of light-years, affecting the intergalactic medium. They blow gas out of galaxies, inhibiting the formation of new stars, and can create huge cavities in the cosmic web, the structure of the universe made up of galaxies and clusters of galaxies connected by filaments of dark matter. But black holes aren't just destroyers. They can also play the role of creators. Their influence on the gravitational field and the distribution of matter can contribute to the formation of new structures in the universe. For example, the interaction between a supermassive black hole and the surrounding gas can trigger processes that contribute to the formation of new stars in galaxies. This makes black holes a kind of conductors of the cosmic symphony. Another surprising aspect of black holes is their potential as energy sources. The gravitational energy that is released when matter falls into a black hole can be much more efficient than nuclear fusion, which powers stars. This opens up fantastic prospects for future interstellar civilizations. If humanity is ever able to learn how to harness the energy of black holes, it could be a solution to the problem of energy resources. Imagine a future where giant space stations orbit a black hole, harvesting its energy. Such a concept, known as the Penrose sphere, is based on the theory that particles that fall into the relativistic field of a rotating black hole can release energy. Although this remains in the realm of fiction for now, ideas related to black holes inspire the development of innovative approaches to solving global problems. No less fascinating is the effect of black holes on time. Near a black hole, time for an outside observer almost stops. This curvature of time opens up surprising prospects for exploring its nature. Perhaps in the future, humans will be able to use black holes for time travel, although for now it feels more like fiction than scientific reality. But even today, black holes make it possible to study gravitational time dilation, which is important for testing general relativity. Black holes can also shed light on the nature of dark matter and dark energy. Some scientists suggest that primordial black holes that originated in the early universe may be part of dark matter. In addition, there are hypotheses that black holes may be associated with dark energy, a force that accelerates the expansion of the universe. While these ideas are speculative for now, they indicate that black holes may be the key to solving the biggest mysteries of cosmology. Black holes not only demonstrate how amazing and complex our universe is, but also show that there are no limits to cognition. They remind us that each new discovery opens up even more questions. In every corner of space, even in its darkest and scariest parts, there is always something worth exploring. This research is ongoing. Each new look at a black hole opens up new horizons for us and makes us think about what else we don't know. Perhaps black holes hide not only the answer to questions about the nature of the universe, but also a clue about our place in it. They are a challenge, an invitation and an inspiration for everyone who tries to understand this boundless and mysterious cosmos. Black holes are an eternal mystery that lurks in the depths of space, forcing us to rethink the boundaries of reality. Their influence is so fundamental that they can be considered not only part of the cosmic landscape, but also key players in the development of the universe. Each black hole is a place where the deepest laws of physics collide, where gravity, space, and time merge into something unfathomable. Imagine a black hole slowly engulfing a star that has come too close to its event horizon. This process looks incredibly dramatic. The heated gas from the star forms a bright accretion disk that glows in the X-ray range. Some of this matter is emitted in the form of powerful jets that spread out thousands of light-years in space. But the rest of matter irrevocably falls beyond the event horizon, disappearing from our gaze. It becomes part of a black hole, increasing its mass and changing its rotation. The rotation of a black hole is another surprising feature. Black holes don't just absorb matter, they can have a colossal angular momentum that occurs due to the rotation of matter falling on them. Rotating black holes, called car black holes, create special effects in the space around them. For example, they cause the phenomenon of dragging space, when the very structure of spacetime rotates along with the black hole. This leads to incredible effects, such as curvature of the trajectories of light and matter passing nearby. Even more intriguing is that black holes can evaporate due to Hawking radiation. This process is very slow for massive black holes, but for smaller black holes, it can be significantly faster. For example, if primordial low-mass black holes formed in the early universe, they could have evaporated even before how we will be able to detect them. But what remains after the black hole has completely evaporated? Is information about the objects it has absorbed stored? Could this process be the key to understanding quantum gravity? The information paradox of black holes is one of the biggest problems of modern physics. It arises because quantum mechanics requires the conservation of information, and general relativity seems to allow it to be destroyed in a singularity. This contradiction has led to the creation of new theories, such as the holographic principle. According to it, all the information that falls into a black hole can be encoded on its event horizon. This information exists as a kind of hologram record that reflects the entire content of the black hole. Every black hole in the universe has its own history. It can occur due to the collapse of a massive star or the merger of smaller black holes. A merger is an event of colossal proportions in which energy equal to the mass of several suns is released in the form of gravitational waves. These waves are a kind of cosmic ricochet that travels through spacetime, carrying information about the masses, rotations, and distances of black holes that have merged. Gravitational waves ushered in a new era in astronomy. They allow us to explore objects that we would never be able to see with traditional methods. For example, thanks to gravitational waves, we can detect black holes that do not interact with matter and therefore remain invisible in conventional telescopes. This makes it possible to create a more complete picture of how black holes are distributed in the universe and how they affect its evolution. The regions of curvature of space and time also pose us with questions about other dimensions. Imagine that our three-dimensional spacetime is just part of a larger, multidimensional universe. Black holes can be a kind of windows into these extra dimensions, although these ideas so far remain speculative. However, they stimulate the development of theories, such as string theory, which tries to unify all the fundamental forces of nature into a single concept. Even centuries after Einstein predicted the existence of black holes, they remain an object that inspires, surprises, and forces you to look for answers to questions that seem unsolvable. What is hidden behind the event horizon? Can we ever look inside without destroying ourselves in the process? And will black holes ever be able to become our allies in trips to the farthest corners of space? These questions may remain unanswered for many years to come. But this is precisely the greatness of science, it never stops searching, even if the answers seem unattainable. Black holes are a reminder that human curiosity and the desire for knowledge have no limits. They are a challenge that pushes us to discovery, and at the same time a door into infinity that we are just beginning to discover. Black holes, as incomprehensible and mysterious phenomena, continue to fuel our imagination and science, opening up new horizons of understanding for humanity. They are the gateway to the deepest cosmic mysteries and may prove to be the key to solving fundamental questions about the nature of the universe. One of the most striking characteristics of black holes is their ability to warp the space and time around them. This distortion is so strong that even light cannot escape its influence. Imagine a beam of light passing near a black hole. Instead of a straight line, it forms a curved trajectory, creating a gravitational lensing effect. Thanks to this effect, we can observe distant galaxies that would otherwise be invisible. The black hole acts as a kind of cosmic lens that magnifies the image of distant objects and allows you to look into the depths of the universe. Imagine another exotic situation, an object that crosses the event horizon of a black hole. From the point of view of an external observer, this object will never reach the event horizon. It will appear frozen in time, turning more and more red until its light goes out completely. But from the point of view of the object itself, time will pass of course, and it will quickly fall into a singularity, where the laws of physics that we know cease to apply. The singularity is the central element of a black hole, a point of infinite density and curvature of spacetime. This is where the theory of relativity ceases to be applicable and there is a need to create a new theory that could describe these extreme conditions. Quantum gravity, which combines quantum mechanics and the theory of relativity, is one of the main contenders for this role. However, its development remains one of the biggest problems of modern science. Another aspect that makes black holes so fascinating is their relationship to thermodynamics. Imagine that black holes have temperature and entropy, as predicted by Stephen Hawking. The entropy of a black hole is proportional to the area of its event horizon, which opens a window to deeper connections between information, quantum processes and gravity. This begs the question: can the universe be a kind of giant information system, where black holes play the role of a kind of quantum servers that store and process information? Some scientists have suggested that black holes could be gateways to other universes. If an object passes through the event horizon, it may not just disappear, but enter a new spacetime, completely different from ours. These theories remain speculative, but they offer interesting opportunities for reflection on the multidimensionality and complex structure of reality. Another prospect is the use of black holes to investigate the quantum nature of gravity. For example, Hawking radiation shows that black holes are not completely black. They emit faint thermal radiation due to quantum effects at the event horizon. This phenomenon, although very slow for massive black holes, could prove critical for understanding the interaction of gravity and quantum fields. No less intriguing is the idea of the existence of primordial black holes that could have arisen immediately after the Big Bang. If they exist, these black holes could be responsible for many phenomena that we don't yet understand, such as the nature of dark matter. Primary black holes can have masses ranging from very small to very large, and studying them can shed light on the early history of the universe. Modern technologies such as the LIGO and Virgo gravitational wave observatories have ushered in a new era in the study of black holes. Thanks to gravitational waves, we can observe events that were inaccessible before: collisions and mergers of black holes, interactions between them, as well as their impact on the surrounding space. These observations allow us to create more and more accurate models of their behavior and impact on the cosmos. Black holes are the place where time stops, matter disappears, and the unknown begins. They demonstrate that the universe is much more amazing than we can imagine, and that each discovery brings with it even more questions. They are a challenge to science, philosophy, and our imagination. They symbolize that even in the darkest corners of space there is something that it is worth studying, something that can change our understanding of reality. Black holes are the keys to infinity that we are just beginning to comprehend. Black holes remain an eternal mystery that humanity is trying to solve, and each new look at them opens up even deeper horizons. They are not only objects of extraordinary power, but also symbols of the absolute limits of our knowledge. Studying black holes is more than just astronomy, it is the search for answers to fundamental questions about the nature of reality, the universe, and our place in it. Imagine a universe where black holes act as a kind of cosmic conductors. They control the distribution of matter and energy, the formation of galaxies, and influence the motion of stars. Supermassive black holes, which are at the centers of galaxies, are the main drivers of these processes. Their gravitational influence is so strong that it is able to form the orbits of millions of stars, creating a stable galaxy structure. But that's only one side of their role. They can also destroy, by absorbing stars or ejecting powerful jets of matter that change the dynamics of the cosmic environment. The accretion disks that form around black holes are some of the hottest and brightest objects in the universe. As matter spins and falls into a black hole, it heats up to millions of degrees, forming a glow that is visible billions of light-years away. This glow can obscure the entire galaxy where the black hole is located, creating objects we call quasars. Quasars are among the brightest beacons in space and allow us to explore the far reaches of the universe, revealing its history. Even more surprising is the phenomenon of relativistic jets. These narrow streams of energy, which are ejected from the poles of the black hole, are the result of the complex interaction of magnetic fields and the rotation of matter in the accretion disk. Jets can penetrate intergalactic space millions of light-years away, affecting clouds of gas and dust from which new stars are formed. They not only destroy, but also create, regulating the processes of star formation and galaxy formation. Equally intriguing is the suggestion that black holes may be connected to other universes or dimensions. Imagine that there is something more lurking behind the event horizon than we can imagine. Some theorists suggest that black holes may be wormholes, tunnels that connect different parts of spacetime or even different universes. Although this idea is speculative for now, it makes us reflect on how complex the structure of reality can be. Modern technology allows us to explore black holes more and more deeply. In 2019, the world first saw an image of the shadow of a black hole's event horizon thanks to the Event Horizon Project telescope. This was a confirmation of many theories and showed how far we have come in the study of these objects. But this is just the beginning. In the future, more powerful telescopes and gravitational wave observatories will make it possible to study even more details, such as rotation, interaction with surrounding matter, and even possible quantum effects. Black holes also pose fundamental philosophical questions to us. What is time? Does it have a beginning and an end? Is spacetime continuous, or does it break down into quanta under extreme conditions? Black holes, with their ability to slow down and even stop time, challenge our usual perception of reality. Imagine that time could flow very differently for objects that are near the event horizon than for those observing from afar. This reminds us that our ideas about reality are only part of a much more complex picture. They also make us think about the nature of information. What happens to information about objects that fall into a black hole? Does it disappear forever, or is it preserved in some way? The holographic principle hypothesis assumes that all information can be encoded on the surface of the event horizon in the form of a two-dimensional record. If this is the case, then black holes are not just objects, but something like cosmic hard drives that store data about the universe. Black holes, for all their mystery and incomprehensibility, are a source of boundless inspiration. They symbolize the idea that the universe is much more complex and interesting than we can imagine. They remind us that each new discovery is just the beginning of a new journey in search of truth. Black holes are a window to infinity that makes us ask questions, look for answers, and never stop marveling at the immensity of space. Black holes remain a source of endless mysteries and scientific discoveries, and the more we investigate them, the more interesting details and unexpected finds are revealed to us. One of the most interesting phenomena associated with black holes is the process of forming gravitational waves. When two black holes merge, they create waves in spacetime itself that propagate at the speed of light. In 2015, it was possible to record these waves for the first time using the LIGO observatory. It was a revolution in physics. Gravitational waves allow you to hear space, observe events that remained invisible before. For example, they can reveal the mass, rotation, and even distance to merging black holes. Another discovery is how black holes interact with the surrounding matter. Supermassive black holes that are at the centers of galaxies can affect the galactic climate. For example, energy emissions in the form of jets can heat gas in galaxies, inhibiting the formation of new stars. But this process also has the opposite effect. Some jets, on the other hand, can compress gas, which stimulates the formation of new stars. This is a kind of game of creation and destruction, where the black hole plays the role of a space architect. The study of relativistic black hole jets is also incredibly interesting. For example, in the galaxy M87, a huge jet stretching for thousands of light-years was observed. This jet of matter is ejected at close to the speed of light and emits radio waves that we can capture. Studying such jets helps to understand how black holes convert gravitational energy into high-energy particle streams. Another interesting area of research is attempts to detect primordial black holes. These are objects that could have arisen immediately after the Big Bang, when the density of matter in the universe was extremely high. They can have different masses, from a few grams to several solar masses. If they exist, it could explain the nature of dark matter, which makes up a large part of the mass of the universe but remains invisible to us. An interesting phenomenon associated with black holes is their connection with mysterious dark energy. Some researchers suggest that black holes may be sources of dark energy, which is responsible for the accelerated expansion of the universe. Although this idea remains hypothetical, it opens up a new direction in cosmology that combines the microcosm of quantum physics with the macrocosm of cosmic evolution. Another area of interest is the possibility of creating artificial black holes in the laboratory. Although it seems fantastic, microscopic black holes could theoretically arise during high-energy experiments, such as at the Large Hadron Collider. Such black holes would be unstable and evaporate rapidly due to Hawking radiation, but their creation could confirm many theories of quantum gravity. The study of the effects that black holes cause in their immediate surroundings cannot be overlooked. For example, at the center of our galaxy, the Milky Way, is the supermassive black hole Sagittarius A star. Astronomers observe the movement of stars near it to study its mass and behavior. One star, S2, orbits Sagittarius A** at an extraordinary speed, which confirmed the predictions of Einstein's theory of relativity. Also worth mentioning are supermassive black holes in other galaxies that form active galactic nuclei. Their behavior changes depending on how much matter they absorb. For example, when the accretion disk around a black hole is depleted, the core becomes less active and gradually falls asleep. This allows us to study the evolution of such objects and their impact on galaxies. Black holes are also objects of artistic inspiration and fantasies. Imagine an interstellar ship that uses a black hole as a source of energy or as a mechanism to accelerate in a journey through space. While such ideas remain in the realm of fiction, they are based on real-world physical principles, such as using gravitational maneuvers to gain extra speed. The study of black holes continues to change our understanding of the universe. They are not only a challenge for science, but also an inspiration for future generations of researchers who will seek answers to questions that seem almost unsolvable. Black holes remind us that the darkest corners of space can hide the brightest truths about our reality. Black holes are not just physical objects, they are among the greatest mysteries of the universe, combining the most complex aspects of cosmology, quantum physics and general relativity. They symbolize the limits of our knowledge and at the same time invite us to overcome them. By studying black holes, we not only expand the boundaries of science, but also face deep philosophical questions about the nature of reality, time and space. Each black hole tells its own story. They arise from the death of stars, are born in terrible cataclysms and absorb everything in their path. But despite their reputation as destroyers, they are also creators. They form galaxies, control the movement of stars, and even influence the evolution of the cosmos as a whole. Their accretion disks and jets are sources of incredible energy that can change the course of cosmic processes. Black holes are also laboratories where we test the limits of our theories. They allow us to study extreme conditions that cannot be created in terrestrial laboratories. They force us to look for new theories that combine quantum mechanics and gravity. They change our understanding of time, space, and information. Hawking radiation, the holographic principle, and the evaporation of black holes are all just the tip of the iceberg in the study of their nature. The future study of black holes promises to be even more exciting. New generations of telescopes and observatories will make it possible to study event horizons with unprecedented precision. Gravitational wave astronomy will pave the way for understanding the invisible aspects of the universe. And maybe someday we will even be able to create miniature black holes in laboratories, which will be a breakthrough in understanding quantum gravity. But like all great mysteries, black holes also make us look inward. They make us think about what cognition means and whether there are limits to this process. Will we ever be able to look beyond the event horizon and see what is now hidden from our eyes? Will we find a way to understand the singularity? Will black holes help reveal the secrets of the beginning of time and the evolution of the universe? Black holes are a mystery that never ceases to arouse fascination and curiosity. They symbolize the unknown and are a guide to new discoveries. Studying them is a journey that forces us to push the boundaries of what is possible, ask the most daring questions, and never stop searching for the truth. And even if the answers seem unattainable, the research process itself brings us more than we could have imagined. Black holes are a reflection of the infinity of the universe and our endless thirst for knowledge. Imagine a light so powerful that it can outshine entire galaxies. A beacon so distant that its glow began its journey to us billions of years ago, at a time when the universe was in its infancy. These extraordinary objects are known as quasars. They are not just celestial phenomena, they are cosmic storytellers, revealing the history and secrets of the universe. Through quasars, we can explore the early stages of the cosmos, uncover the mysteries of black holes, and understand the dynamic processes shaping galaxies and intergalactic space. Quasars, short for quasi-stellar objects, are the blazing cores of distant galaxies. They are powered by supermassive black holes, gigantic cosmic entities with masses millions to billions of times that of our Sun. Despite their name, black holes are far from inactive. They exert an immense gravitational pull, drawing and surrounding matter like gas, dust, and even entire stars. As this matter spirals into the black hole, it forms an accretion disk, a swirling structure that heats up to millions of degrees due to intense friction and gravitational forces. This process releases colossal amounts of energy, which we observe as the radiant light of quasars. The discovery of quasars revolutionized our understanding of the universe. In the 1960s, astronomers were puzzled by mysterious sources of radio waves that didn't correspond to any known stars or galaxies. When Martin Schmidt, a Dutch astronomer, analyzed the light spectrum of one such source, 3C273, he made a groundbreaking realization. The light was redshifted, meaning the object was billions of light-years away, yet it was brighter than an entire galaxy. This finding demonstrated that quasars were not local phenomena but distant cosmic powerhouses. It was a revelation that expanded the known scale of the universe and ushered in a new era of astrophysics. At the heart of every quasar lies a supermassive black hole, an enigmatic entity with gravitational forces so strong that not even light can escape its pull. However, the surrounding accretion disk is where the real drama unfolds. The disk's material, pulled toward the black hole, collides at extreme speeds, generating heat and light that outshine entire galaxies. This radiation spans the electromagnetic spectrum, from radio waves to gamma rays. Some quasars also produce relativistic jets, narrow beams of plasma that shoot out from the black hole's poles at nearly the speed of light. These jets can extend for hundreds of thousands of light-years, interacting with their host galaxies and beyond. Quasars are not just fascinating objects, they are essential tools for understanding the universe. Their light travels vast distances to reach us, carrying information about the cosmos's past. By studying quasars, scientists can peer into the universe's early stages, when the first galaxies and black holes were forming. The light from quasars also interacts with the intergalactic medium, the gas and matter that fills the space between galaxies, providing insights into its composition, temperature, and density. Quasars act as cosmic flashlights, illuminating the structure of the universe and helping us map the large-scale distribution of matter. One of the most remarkable features of quasars is their redshift. As the universe expands, the light from distant objects stretches, shifting toward longer wavelengths. The higher the redshift, the farther away, and older, the object is. Some quasars have redshifts so high that their light was emitted when the universe was less than 1 billion years old. These ancient quasars provide a glimpse into a time when the cosmos was just beginning to take shape. For example, ULA's J1342+0928, located 13.1 billion light-years away, offers valuable insights into the reionization era, a period when the first stars and galaxies transformed the universe from a dark, neutral state into one filled with light. Quasars also challenge our understanding of supermassive black holes. The sheer size and luminosity of some quasars suggest that their central black holes grew incredibly quickly, raising questions about how such massive objects formed in the early universe. Did they originate from the collapse of massive primordial stars, or did they form through direct gas accretion? These mysteries drive ongoing research and fuel the development of new theories. Famous quasars like 3C273, the first recognized quasar, continue to be key subjects of study. Located 2.4 billion light-years away, 3C273 is visible in amateur telescopes and remains a cornerstone of our understanding of cosmic distances. Another notable example, SDSS-J0100 plus 2802, houses a black hole 12 billion times the mass of the Sun. This extraordinary quasar challenges existing models of black hole growth, as it appears to have reached its massive size in a relatively short time after the Big Bang. Quasars are not static, they are dynamic participants in the evolution of their host galaxies. The jets and winds they emit can have profound effects on their surroundings. These outflows can heat interstellar gas, preventing it from cooling and condensing into stars. In some cases, however, they compress gas clouds, triggering bursts of star formation. This dual influence makes quasars both creators and regulators within their galactic environments. The study of quasars has also advanced our understanding of dark matter and dark energy. Through phenomena like gravitational lensing, where a massive object bends the light of a quasar, scientists can map the distribution of dark matter. Quasars also help refine measurements of the universe's expansion, shedding light on dark energy's role in driving this acceleration. By mapping the large-scale distribution of quasars, researchers gain insights into how these mysterious forces shape the cosmos. Despite decades of research, many questions about quasars remain unanswered. How do supermassive black holes form and grow so rapidly? How many quasars are hidden behind dense clouds of gas and dust, invisible to our current telescopes? Could some quasars be powered by binary black holes, offering clues about the dynamics of galaxy mergers? These mysteries continue to inspire scientists and push the boundaries of what we know. Quasars also hold a unique place in human imagination. They are symbols of infinity and exploration, representing the vastness of the cosmos and the unyielding drive to uncover its secrets. In science fiction, quasars are often depicted as sources of limitless energy or gateways to other dimensions. In reality, they challenge us to think about the universe's ultimate nature and our place within it. The future of quasar research is bright. New technologies, such as the James Webb Space Telescope, promise to uncover quasars from the universe's earliest epochs, providing unprecedented insights into the formation of black holes and galaxies. Advanced simulations and machine learning algorithms are helping scientists model the behavior of quasars and their impact on their surroundings. These efforts will not only deepen our understanding of quasars but also illuminate broader cosmic processes. Quasars remind us that the universe is a place of wonder and discovery. They are not just objects of scientific inquiry but also beacons of inspiration, guiding us toward a deeper understanding of existence. As we study quasars, we look not only into the distant past but also into the future of what humanity can achieve. Each discovery brings us closer to unraveling the mysteries of the cosmos and understanding our role in this vast, interconnected universe. Quasars are more than just objects of scientific study, they are cosmic storytellers. Each quasar, with its immense brightness and incredible distance, carries a tale of a time when the universe was vastly different from what we see today. But how can something so far away and so mysterious continue to captivate scientists and dreamers alike? The answer lies in their ability to bridge the gap between the known and the unknown, between the present and the distant past, and between the ordinary and the extraordinary. Imagine this: A quasar's light began its journey billions of years ago, traveling across the expanding universe, passing through clouds of gas, skirting by galaxies, and finally reaching Earth. By the time this light touches the lenses of our telescopes, it has carried with it a story of transformation and evolution. It tells us what the universe was like when it was only a fraction of its current age, a time when galaxies were forming, and supermassive black holes were first taking shape. Every photon of light from a quasar is a piece of a cosmic puzzle, waiting to be unraveled. But quasars are not just passive narrators, they are active participants in shaping the universe. Their immense energy and power influence the galaxies that host them, the intergalactic medium they illuminate, and even the large-scale structure of the cosmos. For example, the jets emitted by quasars are not mere cosmic fireworks, they are engines of change. These jets can heat the gas in their host galaxies, suppressing the formation of new stars. On the other hand, they can also compress clouds of gas, sparking bursts of star formation in distant regions. This dual role, both as destroyers and creators, makes quasars unique architects of the universe. Take a moment to consider the raw power of a quasar. The brightest quasars outshine entire galaxies, emitting more energy in a single second than all the stars in the Milky Way combined. If we could harness even a fraction of this energy, it would be enough to power civilizations for millions of years. While such an idea remains firmly in the realm of science fiction, it sparks a tantalizing question: could advanced civilizations in the universe be doing exactly that? Could quasars be natural sources of energy for civilizations far more advanced than ours? This idea is not as far-fetched as it seems. In the field of astroengineering, scientists speculate about megastructures like Dyson spheres, hypothetical constructs that could surround a star or even a quasar, capturing its energy output. While no such structures have been observed, the very possibility fuels our imagination and reminds us of the boundless potential of human ingenuity. Quasars also serve as signposts in the vast cosmic expanse, acting as celestial lighthouses for interstellar navigation. Their unique brightness and fixed positions make them ideal reference points for mapping the universe. Imagine future spacecraft venturing into the galaxy, using quasars as beacons to orient themselves and navigate through the stars. In this sense, quasars are not just remnants of the distant past, they are guides for our potential future. But perhaps the most awe-inspiring aspect of quasars is their ability to connect us to the deepest mysteries of the cosmos. They challenge us to think about the origins of supermassive black holes, the nature of dark matter and dark energy, and the ultimate fate of the universe. Some quasars, with their extraordinary brightness and puzzling properties, even raise questions about the very laws of physics. Are our current theories complete, or do quasars hint at phenomena we have yet to understand? In the vast tapestry of the cosmos, quasars stand out as luminous threads that weave together the story of creation, transformation, and discovery. They remind us of the incredible scale of the universe and the interconnectedness of all things. Each photon of light from a quasar, no matter how distant or ancient, carries with it a message, that the universe is vast, mysterious, and full of wonders waiting to be discovered. As we continue to explore the universe, quasars will remain key players in our quest for understanding. They challenge us to push the boundaries of what we know, to develop new technologies, and to ask bigger questions. In doing so, they inspire not only scientists but also anyone who has ever looked up at the night sky and wondered about the nature of existence. Imagine a future where we have unlocked the secrets of quasars. Perhaps we will use their energy to power interstellar voyages, or perhaps we will understand how they helped shape the galaxies that gave birth to stars, planets, and life itself. One thing is certain: quasars will continue to light the way, guiding us toward new discoveries and reminding us of the limitless possibilities of the universe. So the next time you look at the night sky, remember that beyond the stars lies a realm of unimaginable power and beauty. Somewhere out there, a quasar is shining, a cosmic beacon that has traveled billions of years to tell its story. And in listening to that story, we not only learn about the universe but also about ourselves and our place within this infinite expanse. Quasars are more than just bright objects scattered across the distant cosmos. They are dynamic, evolving phenomena that reveal the universe's interconnected processes. To understand their full impact, let us dive deeper into how quasars affect their surroundings, influence their host galaxies, and contribute to the grand tapestry of the cosmos. Imagine a quasar's relativistic jets, narrow, focused beams of plasma launched from near the poles of a black hole. These jets move at speeds approaching the speed of light, slicing through the surrounding intergalactic medium. As they travel, they interact with clouds of gas, heating them to extreme temperatures and altering their composition. These jets are not just destructive, they play a dual role in the cosmos. While they can suppress star formation by driving gas out of their host galaxy, they can also trigger the birth of new stars by compressing gas in distant regions. This paradoxical behavior makes quasars both destroyers and creators, sculpting their galaxies and the space beyond. Let's take a closer look at a fascinating concept: the life cycle of a quasar. Quasars do not remain in their highly luminous state forever. They are born during periods of intense galactic activity, often triggered by the collision or merger of galaxies. When two galaxies collide, their central black holes begin to consume massive amounts of gas and dust, igniting a quasar. This period of activity can last for millions of years, during which the quasar shines as one of the brightest objects in the universe. Over time, as the available gas and dust are consumed or ejected by the quasar's powerful winds and jets, the activity decreases. The quasar eventually fades, leaving behind a dormant black hole at the galaxy's center. This process helps explain why many galaxies, including our own Milky Way, have massive black holes that are no longer active. Quasars are also invaluable tools for probing the universe's history. By studying the light from quasars, astronomers can learn about the early universe, when the first stars and galaxies formed. During this epoch, known as the reionization era, the universe transitioned from a dark, neutral state to one filled with light and ionized gas. Quasars played a crucial role in this transformation. Their intense radiation helped reionize the surrounding hydrogen gas, allowing light to travel freely through the universe for the first time. By observing distant quasars, scientists can trace the timeline of this pivotal era and better understand how the universe became what it is today. But quasars do not only illuminate the past, they also offer glimpses into some of the universe's most elusive phenomena, such as dark matter and dark energy. Dark matter, an invisible substance that makes up most of the universe's mass, cannot be observed directly. However, its gravitational effects can be detected through quasars. When the light from a quasar passes near a massive object like a galaxy or galaxy cluster, the gravitational field of that object bends the light, creating a phenomenon known as gravitational lensing. This effect not only magnifies the quasar's light but also provides critical insights into the distribution of dark matter in the intervening object. Dark energy, on the other hand, is responsible for the accelerating expansion of the universe. Quasars, with their extreme brightness and vast distances, serve as cosmic markers that help scientists measure how the universe's expansion rate has changed over time. By mapping the positions of quasars and studying their redshifts, researchers can refine models of how dark energy influences the cosmos. These studies bring us closer to answering one of the most profound questions in modern science: what is the fate of the universe? Quasars also challenge our understanding of black hole formation. How did the supermassive black holes powering quasars grow so large so quickly in the early universe? Theories suggest that they may have formed from the collapse of massive primordial stars or through the direct accretion of gas. However, neither explanation fully accounts for the rapid growth observed in some quasars, like SDSS-J0100 plus 2802, whose central black hole reached a mass of 12 billion suns just a few hundred million years after the Big Bang. These enigmatic objects continue to push the boundaries of our understanding, driving new theories and observations. For all their complexity, quasars are also reminders of the universe's grandeur and scale. They are among the most distant objects we can observe, with some quasars located over 13 billion light-years away. The light we see from these quasars began its journey long before Earth even existed. By studying quasars, we connect with a time when the universe was in its infancy, offering a humbling perspective on our place in the cosmos. Quasars also serve as a source of inspiration. Their power, beauty, and mystery have captured the imagination of countless people, from scientists to artists to writers. In science fiction, quasars often represent the ultimate energy source, fueling interstellar civilizations or serving as gateways to other dimensions. In reality, they inspire us to think about what is possible and to dream of exploring the universe in ways we cannot yet fully comprehend. The future of quasar research is filled with promise. New telescopes, like the James Webb Space Telescope, are poised to uncover quasars from the earliest epochs of the universe, shedding light on how the first black holes and galaxies formed. Advances in computational modeling and machine learning are enabling scientists to simulate the behavior of quasars and their impact on their surroundings with unprecedented precision. These tools will not only deepen our understanding of quasars but also help solve broader mysteries, such as the nature of dark matter and the processes that govern galaxy formation. As we continue to study quasars, we are reminded of the boundless potential of human curiosity. Each discovery brings us closer to understanding the universe's origins, evolution, and ultimate destiny. Quasars are more than just objects of study, they are symbols of exploration and discovery, guiding us toward new horizons. So the next time you look up at the night sky, remember that beyond the stars lies a realm of unimaginable power and beauty. Somewhere out there, a quasar is shining, a cosmic beacon that has traveled billions of years to reach us. Through its light, we glimpse not only the universe's past but also its infinite possibilities. Imagine a universe untouched by starlight, a vast expanse of darkness stretching endlessly in every direction. This was the cosmos just after the Big Bang, a time before stars, galaxies, and the light they would bring into existence. Then, something extraordinary happened. Gravity began sculpting the first structures from the primordial chaos. Clouds of hydrogen collapsed to form the first stars, which ignited like cosmic fireworks. These stars grouped into young galaxies, and at their centers, something even more profound began to emerge, the first supermassive black holes. It was these cosmic titans, surrounded by disks of glowing matter, that would evolve into quasars, the brightest beacons in the universe. Quasars are not just bright objects, they are cosmic storytellers. Each quasar is like a window into the distant past, offering a glimpse of a time when the universe was still forming. The light from quasars began its journey billions of years ago, crossing vast stretches of space to reach us. By the time it arrives, it carries with it secrets of a universe that no longer exists as it once did. At the heart of every quasar lies a supermassive black hole, a gravitational force so immense that not even light can escape its pull. But contrary to what we might imagine, black holes are not simply dark voids that swallow everything. They are engines of creation and destruction, surrounded by swirling disks of gas and dust called accretion disks. These disks are where the magic happens. As matter spirals inward, friction and gravitational forces heat it to millions of degrees, causing it to glow with unimaginable brilliance. This glow is what we observe as the light of a quasar. But quasars are not just beautiful, they are powerful. The energy released by a single quasar can outshine an entire galaxy of stars. Some quasars emit jets of plasma that travel at nearly the speed of light, extending for hundreds of thousands of light-years. These jets are so powerful that they can pierce the intergalactic medium, altering the environment of their host galaxies and even neighboring ones. It's as if quasars are not content to merely exist, they must shape the universe around them. Take, for example, 3C273, the first quasar ever identified. Located 2.4 billion light-years away, it revolutionized our understanding of the universe's scale. Its discovery in 1963 by Martin Schmidt proved that quasars were not just peculiar stars but cosmic beacons from the far reaches of space. Since then, quasars like ULA's J1342 plus 0928, which dates back to the universe's infancy, and SDSS J0100 plus 2802, with its black hole 12 billion times the Sun's mass, have pushed the boundaries of what we thought was possible. One of the most fascinating aspects of quasars is their role in the evolution of galaxies. Galaxies are not static, they are living systems that grow, collide, and change over time. Quasars are often born in the chaotic aftermath of galaxy mergers. When two galaxies collide, their central black holes begin consuming enormous amounts of matter, igniting a quasar. This activity can last millions of years, after which the quasar's fuel runs out, and it fades into dormancy. What remains is a massive but quiet black hole, a relic of its once glorious past. Quasars are also essential for studying the universe's history. During the reionization era, when the first stars and galaxies began lighting up the cosmos, quasars played a pivotal role. Their intense radiation ionized the surrounding hydrogen gas, transforming the universe from a dark, opaque state into one filled with light. By observing distant quasars, astronomers can piece together the timeline of this transformation, gaining insights into how the cosmos evolved into the structure we see today. But quasars are not just cosmic relics, they are active participants in shaping the universe. Their jets and winds can regulate star formation within their host galaxies. In some cases, they expel gas, preventing new stars from forming. In others, they compress gas clouds, triggering bursts of star formation. This dual role makes quasars both destroyers and creators, influencing the life cycles of galaxies and the stars within them. Quasars also serve as tools for exploring some of the universe's greatest mysteries. For instance, their light interacts with the intergalactic medium, revealing the distribution of matter across vast distances. This interaction creates patterns in their spectra, known as the Lyman alpha forest, which scientists use to map the large-scale structure of the universe. Even more intriguing is how quasars help us study phenomena we cannot directly observe, like dark matter and dark energy. When the light from a quasar passes near a massive object, such as a galaxy cluster, the object's gravity bends the light, creating a phenomenon known as gravitational lensing. This effect not only magnifies the quasar's light but also provides a way to map the invisible distribution of dark matter in the lensing object. Dark energy, the mysterious force driving the universe's accelerated expansion, is another area where quasars play a crucial role. By studying the distribution and redshifts of quasars, scientists can refine their models of how dark energy influences the cosmos over time. These studies bring us closer to understanding the ultimate fate of the universe. Despite everything we've learned, quasars remain deeply mysterious. How do their black holes grow so massive so quickly? How many quasars are hidden behind dense clouds of gas and dust, invisible to our telescopes? Could some quasars harbor pairs of black holes, orbiting each other in a cosmic dance? These questions drive the development of new telescopes and observational techniques, pushing the boundaries of what we can see and understand. Quasars also inspired the imagination. In science fiction, they are often depicted as energy sources for advanced civilizations or as gateways to other dimensions. While these ideas remain speculative, they remind us of the boundless potential of exploration and discovery. As we look to the future, the study of quasars promises to unlock even more secrets. The James Webb Space Telescope is set to reveal quasars from the earliest epochs of the universe, shedding light on the birth of black holes and galaxies. Advanced simulations and machine learning tools are helping scientists model the behavior of quasars with unprecedented detail, providing new insights into their role in cosmic evolution. Quasars are not just objects of scientific inquiry, they are symbols of the universe's vastness and beauty. They remind us of how much we have discovered and how much remains unknown. They challenge us to think beyond our limits and inspire us to dream of what lies beyond the stars. As you gaze at the night sky, consider this: beyond the stars you see lies a realm of unimaginable power and beauty. Somewhere, a quasar is shining, its light traveling billions of years to reach us. Through that light, we glimpse not only the past but also the infinite possibilities of the future. Quasars are more than cosmic beacons, they are guides to the mysteries of existence, illuminating the path toward understanding and discovery. Quasars are powered by processes so extreme they seem almost supernatural. At their core lies a supermassive black hole, whose mass can range from millions to billions of times that of our Sun. These black holes are surrounded by an accretion disk, a swirling, chaotic structure of gas, dust, and even stars being pulled in by the black hole's immense gravity. The physics of an accretion disk is what makes quasars shine so brightly. As matter spirals inward, it is compressed and heated to millions of degrees. This heat generates light across the electromagnetic spectrum, from visible light to ultraviolet, X-rays, and even gamma rays. The efficiency of this energy conversion is astonishing. Up to 10% of the infalling matter's mass is transformed into energy. For comparison, nuclear fusion, the process that powers stars, converts only about 0.7% of mass into energy. But the black hole doesn't consume all the matter around it. Some of it is ejected at incredible speeds in the form of relativistic jets. These jets are composed of charged particles, accelerated to velocities approaching the speed of light. Emerging perpendicular to the accretion disk, they extend for hundreds of thousands, and in some cases, millions of light-years. The exact mechanism that creates these jets is still a mystery, but scientists believe that magnetic fields twisted by the spinning accretion disk play a critical role. These jets can carry more energy than billions of stars combined, influencing the surrounding environment on a galactic scale. Relativistic jets are one of the most spectacular features of quasars. These streams of plasma are not only beautiful but also incredibly powerful, capable of shaping the fate of entire galaxies. Near light speeds, the particles in these jets travel at speeds close to that of light, making them some of the fastest moving matter in the universe. Energy output: the jets can transport energy equivalent to the output of 1 billion stars, depositing it into the intergalactic medium. Shock waves: as the jets plow through gas clouds, they create shock waves that compress and heat the gas, sometimes triggering star formation. Relativistic jets also extend far beyond the host galaxy, reaching into the intergalactic medium. These jets interact with the large-scale structure of the universe, the cosmic web, which is made up of vast filaments of gas and dark matter. By injecting energy into this web, jets may influence how galaxies form and evolve within these filaments. Magnetic fields are a key player in the physics of quasars. They help channel the energy from the accretion disk into the relativistic jets. Observing the polarization of light from quasars has allowed scientists to map these magnetic fields, revealing their complex, twisted structures. Understanding how these fields operate could unlock answers to some of the most challenging questions in astrophysics, including how jets are launched and maintained. Quasars are more than just luminous objects, they are windows into the universe's distant past. The light we see from quasars began its journey billions of years ago, long before Earth even existed. By studying quasars, astronomers can learn about the conditions of the early universe. One of the most significant periods in the universe's history is the reionization era, which occurred around 400 to 800 million years after the Big Bang. Before this time, the universe was filled with neutral hydrogen gas, which blocked light. As the first stars and galaxies formed, their light began to ionize this hydrogen, making the universe transparent. Quasars played a crucial role in this process by emitting intense ultraviolet radiation that ionized vast regions of space. Observing quasars from this era helps scientists map the timeline of reionization and understand how the universe transitioned from darkness to light. Despite decades of study, quasars remain some of the most enigmatic objects in the universe. Here are a few of the most intriguing questions they pose. Some quasars, like ULA's J1342+0928, have black holes that reached billions of solar masses in less than 1 billion years after the Big Bang. This rapid growth is difficult to explain. Current theories suggest two possibilities: bypassing the slower process of star formation and collapse. Super-efficient accretion: these black holes may have consumed matter at rates much direct collapse. Some black holes may have formed directly from massive gas clouds, higher than previously thought possible. Many quasars are obscured by thick clouds of gas and dust, making them invisible in optical light. Infrared and X-ray telescopes, like the James Webb Space Telescope and Chandra X-ray Observatory, are helping to uncover these hidden quasars, revealing a more complete picture of the universe's active galactic nuclei. In galaxies that have merged, it's possible that two supermassive black holes exist in close proximity, each contributing to the quasar's activity. Detecting such binary systems could provide insights into how galaxies and black holes evolve during mergers. Quasars are not passive residents of their host galaxies. They actively shape their environments in profound ways. The intense winds and radiation from quasars can heat or expel gas from their host galaxies, depriving them of the material needed to form new stars. This process, known as quasar feedback, is thought to explain why massive galaxies often have little star-forming activity. In some cases, the jets and outflows from quasars compress gas clouds, triggering bursts of star formation. This dual role, both suppressing and stimulating star formation, makes quasars complex agents of change in galactic evolution. Quasars are also key tools for studying dark matter, the mysterious substance that makes up about 27% of the universe. When light from a quasar passes through a massive object like a galaxy cluster, the dark matter in the cluster's gravitational field bends the light, creating a phenomenon called gravitational lensing. This effect not only magnifies the quasar's light but also provides clues about the distribution of dark matter. The study of quasars is far from over. As technology advances, new telescopes and observational techniques will allow us to learn even more about these extraordinary objects. James Webb Space Telescope, set to reveal the earliest quasars, providing insights into the formation of the first galaxies and black holes. Square Kilometer Array, SKA, a radio telescope that will detect faint radio signals from distant quasars, mapping the universe in unprecedented detail. Quasars are more than scientific curiosities, they are symbols of human ingenuity and curiosity. They remind us of the vastness of the cosmos and our desire to understand it. Each quasar we study brings us closer to answering fundamental questions about the universe's origins, evolution, and ultimate fate. As you look up at the night sky, consider this: beyond the stars you see lies a realm of unimaginable power and mystery. Quasars, with their brilliance and distance, connect us to the farthest reaches of space and time. They are not just cosmic beacons, they are guides, illuminating the path toward discovery and understanding. When we look at a quasar, we're not just observing an object, we're witnessing an event that unfolded billions of years ago. It's like peering through a cosmic time machine, catching a glimpse of the universe in its infancy. Each quasar's light began its journey long before the Earth formed, long before our Sun ignited. This light crossed the cosmic web, skimming past galaxy clusters and interstellar voids, carrying with it the story of a universe still finding its form. Think about this: the light from a quasar located 12 billion light-years away began its journey when the universe was only a fraction of its current age, barely 1 billion years old. During this time, the first galaxies were clumping together, and primordial stars were just beginning to shine. By studying quasars, we're effectively unlocking a visual archive of the cosmos, unraveling secrets hidden in the folds of time. Quasars don't exist in isolation. They are born in the chaotic hearts of galaxies, often during galaxy collisions. When two galaxies merge, their central black holes engage in a gravitational ballet, consuming vast reservoirs of gas and dust. This feeding frenzy ignites the quasar, producing the dazzling light we observe across billions of light-years. Imagine two galaxies hurtling toward each other, each with billions of stars, swirling gas clouds, and, at their centers, supermassive black holes. As the galaxies collide, gravitational forces tear apart their structures, sending gas spiraling into the central regions. The supermassive black holes begin to gorge on this material, triggering the birth of a quasar. The collision not only sparks this luminous phenomenon but also reshapes the galaxies, creating new star-forming regions and sometimes flinging stars into intergalactic space. This cosmic drama is not rare. Our own Milky Way galaxy is destined to collide with the Andromeda galaxy in about 4 billion years. When that happens, the central black holes of both galaxies may ignite, forming a quasar that could rival the brightness of the entire night sky. Quasars are not passive lights in the darkness, they are active participants in shaping the cosmos. Their energy output is so immense that it influences the behavior of matter on scales far beyond their host galaxies. Through their jets, winds, and radiation, quasars sculpt the very fabric of the universe. The energy emitted by a quasar often drives colossal winds, powerful enough to expel billions of solar masses of gas from its host galaxy. These winds can travel at speeds of thousands of kilometers per second, sweeping through the galaxy and beyond. This process, known as quasar feedback, plays a crucial role in galactic evolution. Suppressing star formation, by ejecting gas, quasars prevent the galaxy from forming new stars, effectively quenching it. This is why many massive galaxies in the universe today are filled with older stars but lack young, vibrant ones. Triggering starbursts, in some cases, the same winds can compress gas clouds, igniting bursts of star formation in distant regions. It's a paradox. Quasars can destroy and create in equal measure. For every brilliant quasar we observe, there may be countless more hidden from view, shrouded by thick clouds of dust and gas. These obscured quasars are like cosmic secrets, waiting to be unveiled by new technologies. Infrared telescopes like the James Webb Space Telescope are designed to pierce through these veils, revealing quasars that were invisible to previous generations of astronomers. The discovery of these hidden quasars is reshaping our understanding of the universe. They suggest that quasars might have been even more common in the early universe than we previously thought. These obscured quasars also provide clues about the environments in which black holes grow, offering a more complete picture of cosmic evolution. Quasars are intimately connected to the largest structures in the universe, the cosmic web. This web is an intricate network of filaments made of gas, dark matter, and galaxies, stretching across billions of light-years. Quasars illuminate this web, acting like cosmic lighthouses that reveal its structure. When light from a quasar travels through the universe, it encounters clouds of hydrogen gas. These clouds absorb specific wavelengths of light, leaving behind dark lines in the quasar's spectrum. This phenomenon, known as the Lyman alpha forest, allows scientists to map the distribution of hydrogen gas across the universe. It's like tracing the invisible threads of the cosmic web, uncovering the vast interconnectedness of galaxies, filaments, and voids. Quasars have become invaluable tools for studying two of the universe's greatest mysteries, dark matter and dark energy. These phenomena, though invisible, dominate the cosmos, shaping its structure and destiny. Dark matter is a mysterious substance that makes up about 27% of the universe. It doesn't emit, absorb, or reflect light, making it impossible to observe directly. However, its gravitational effects can be studied through quasars. When the light from a quasar passes near a massive object, like a galaxy or galaxy cluster, the dark matter's gravity bends the light, creating a phenomenon known as gravitational lensing. By analyzing these lenses, scientists can map the distribution of dark matter, revealing its role in shaping galaxies and clusters. Dark energy, which makes up about 68% of the universe, is driving its accelerated expansion. Quasars are helping scientists study this mysterious force. By observing the positions and redshifts of quasars, researchers can measure how the universe's expansion rate has changed over time. These observations are crucial for understanding the ultimate fate of the cosmos. The immense power of quasars has led some scientists to speculate about their potential use by advanced extraterrestrial civilizations. If a civilization were capable of harnessing the energy of a quasar, it could achieve levels of power far beyond anything we can currently imagine. A Dyson sphere is a hypothetical megastructure that could surround a star, or in this case, a quasar, to capture its energy. While such structures remain in the realm of science fiction, they provide a fascinating thought experiment. If an advanced civilization were to construct such a sphere around a quasar, it could potentially power interstellar travel, massive computational projects, or even terraforming on a galactic scale. The next few decades promise to be a golden age for quasar studies. With new technologies and observational tools, we are on the brink of uncovering even more secrets about these enigmatic objects. James Webb Space Telescope, JWST, already delivering breathtaking insights. This telescope will continue to reveal quasars from the earliest epochs of the universe, helping us understand the birth of black holes and galaxies. Square Kilometer Array, SKA. This radio telescope will map faint radio signals from distant quasars, offering new insights into the early universe. Euclid Space Telescope, focused on dark energy, Euclid will use quasars to refine measurements of the universe's expansion. Quasars are not just objects of scientific study, they are symbols of the infinite. They remind us of the scale and beauty of the universe, as well as our capacity to comprehend it. They challenge us to think about our place in the cosmos and inspire us to push the boundaries of exploration and discovery. Every quasar is a reminder of the power of curiosity. It tells us that there is always more to learn, more to explore, and more to discover. As we continue to study quasars, we are not only uncovering the secrets of the universe but also reflecting on the nature of existence itself. So, when you look up at the stars tonight, remember, beyond those points of light lie quasars, cosmic beacons that have traveled billions of years to reach us. They are whispers from the past, messages from the universe, and guides to the infinite future. Quasars are among the universe's most captivating enigmas, their brilliance outshining galaxies and their mysteries challenging the boundaries of our understanding. To truly grasp the significance of quasars, imagine standing on a planet billions of light years away, gazing at the night sky as one of these extraordinary beacons dominates the horizon. Its light, intense and unwavering, is not just a spectacle but a testament to the incredible forces shaping the cosmos. Every quasar is powered by a supermassive black hole, an entity so dense that even light cannot escape its grasp. Yet, paradoxically, this darkness is surrounded by unparalleled brilliance. Matter spiraling into the black hole is caught in a maelstrom of extreme forces, heated to millions of degrees as it hurtles inward. The result is an eruption of light and energy so immense that it dwarfs entire galaxies. The accretion disk, the glowing region around the black hole, becomes a furnace of cosmic proportions, releasing radiation across the spectrum. This light travels billions of years to reach us, carrying with it the story of the universe's past. But quasars are not solitary storytellers, they are agents of transformation. Their power extends far beyond their cores, influencing the galaxies they inhabit and the space between. The relativistic jets that emerge from some quasars are like cosmic lances, piercing through intergalactic space and altering everything in their path. These jets, composed of charged particles moving at near-light speeds, carry energy that can heat, compress, or expel gas within their host galaxies. In doing so, they shape the destiny of stars yet to be born, determining whether a galaxy thrives with new star formation or becomes dormant and quiet. The light from a quasar is not just a beacon, it is a probe that interacts with everything it encounters. As it journeys across the universe, it passes through intergalactic clouds of gas, leaving traces of these encounters in its spectrum. Scientists decipher these spectral lines like archaeologists studying ancient artifacts, piecing together a map of the universe's vast structure. This map reveals the cosmic web, an intricate network of galaxies, gas, and dark matter that connects the universe on a grand scale. Quasars illuminate this web, making the invisible visible. What makes quasars even more extraordinary is their role as time travelers. Observing a quasar is like looking into a cosmic mirror reflecting the universe as it was billions of years ago. The light we see today began its journey when the universe was young, a chaotic place where the first galaxies were colliding and merging. By studying quasars, scientists gain a window into these formative epochs, understanding how galaxies and black holes grew together in a symbiotic dance of creation and destruction. The journey of quasar light across billions of years is not without obstacles. Some quasars are hidden from our view, cloaked in shrouds of dust and gas. These obscured quasars are like cosmic whispers, their light muffled but still detectable by specialized telescopes. The James Webb Space Telescope, with its infrared vision, is uncovering these hidden giants, revealing a universe even more active and dynamic than we imagined. These discoveries hint that quasars were far more common in the early universe, playing a crucial role in shaping its evolution. Beyond their scientific significance, quasars inspire profound philosophical questions. Their immense power and unfathomable distances remind us of the vastness of the cosmos and our place within it. They challenge us to think about time on a scale that dwarfs human history, to consider the processes that have been at work for billions of years before our existence. Quasars are both humbling and awe-inspiring, symbols of a universe that is as mysterious as it is beautiful. The connection between quasars and black holes also brings to mind some of the universe's most puzzling phenomena, such as dark matter and dark energy. While dark matter cannot be seen directly, its gravitational influence can be detected in the bending of quasar light as it passes near massive objects. This bending, known as gravitational lensing, allows scientists to map the invisible scaffolding of the universe. Meanwhile, the distribution of quasars across vast cosmic distances provides clues about the influence of dark energy, the force driving the accelerated expansion of the universe. These connections make quasars essential tools for unraveling some of the universe's deepest mysteries. But quasars are not just tools for science, they are also the stuff of imagination. Their power has inspired countless works of science fiction, where they are often portrayed as sources of limitless energy or gateways to other dimensions. The idea of advanced civilizations harnessing the energy of a quasar is a tantalizing one. Such a civilization might build a megastructure around a quasar, capturing its immense output to fuel interstellar travel or power entire planets. While this remains speculative, it underscores the extraordinary nature of quasars as objects that stretch the limits of possibility. The study of quasars is also a testament to human ingenuity. From the first discovery of 3C273 to the cutting-edge observations of modern telescopes, our ability to understand these distant phenomena has grown exponentially. Each new discovery about quasars is a reminder of how far we've come and how much there is still to learn. The more we uncover, the more questions arise, driving the relentless pursuit of knowledge. As technology advances, the future of quasar research promises even greater revelations. Upcoming telescopes like the Square Kilometre Array will detect the faintest radio signals from the universe's early days, while new simulations will model the complex interactions between quasars and their environments with unprecedented detail. These tools will not only deepen our understanding of quasars but also shed light on the origins of galaxies, the formation of supermassive black holes, and the evolution of the universe itself. Quasars remind us that the universe is a place of infinite wonder. They are not just objects of study, they are symbols of the human spirit's drive to explore and understand. Every photon of quasar light that reaches us carries a message from the cosmos, a story of creation, transformation, and resilience. These beacons from the depths of space connect us to a universe that is at once ancient and ever-changing. As you look up at the night sky, remember that beyond the stars lies a realm of unimaginable power and mystery. Somewhere out there, a quasar is shining, its light traveling across the ages to reach us. It is a reminder of the vastness of existence, the beauty of the unknown, and the limitless potential of discovery. In the glow of a quasar, we find not just the story of the universe but also the story of ourselves, curious beings, forever reaching for the light. The universe, vast and infinite, holds its most profound secrets in the light of quasars. These cosmic giants are more than mere phenomena, they are the architects of the cosmos, the witnesses to its birth, and the harbingers of its evolution. Each quasar, with its boundless energy and incomprehensible distance, stands as a sentinel of the ancient universe, a time capsule carrying the echoes of creation. As the light of a quasar begins its journey, it traverses a landscape that is both dynamic and fragile. It weaves through intergalactic clouds, its path distorted by massive objects, and passes by galaxies shaped by collisions and the gravitational pull of dark matter. Every interaction leaves an imprint on the quasar's light, a subtle clue that scientists decode to piece together the universe's history. These interactions reveal the universe's large-scale structure, the cosmic web, a vast network of filaments and voids stretching across billions of light-years. Quasars act as lighthouses in this web, illuminating its intricate connections and helping us map its vastness. The cosmic web itself is a marvel. It is a tapestry woven from galaxies, stars, and dark matter, all bound together by the mysterious force of gravity. At its intersections lie galaxy clusters, the bustling cities of the universe, where the interplay of matter and energy gives rise to some of the most dramatic events in the cosmos. Quasars, situated in these dense regions, influence their surroundings in profound ways. Their jets and winds inject energy into the intergalactic medium, stirring it like a cosmic storm and redistributing gas and matter across vast distances. But quasars are not only confined to their role as cosmic illuminators. They are also harbingers of transformation, their power reshaping the very galaxies that give them life. Picture a young galaxy, chaotic and brimming with gas and dust, its central black hole feeding voraciously on its surroundings. As the black hole consumes this material, the quasar ignites, releasing a torrent of energy that sweeps through the galaxy. This energy can push away the gas needed for star formation, effectively halting the galaxy's growth. Yet, in some cases, this same energy compresses clouds of gas, triggering bursts of new star formation. It's a delicate balance, a cosmic tug-of-war between creation and destruction. The influence of quasars extends beyond their host galaxies, reaching into the intergalactic medium that fills the space between galaxies. This medium, composed mostly of hydrogen gas, is the raw material from which stars and galaxies are formed. Quasars play a pivotal role in shaping its properties. Their radiation ionizes the gas, heating it and altering its composition. By studying the light from quasars as it passes through this medium, scientists can measure its density, temperature, and chemical makeup. This information provides a window into the conditions that prevailed in the early universe, offering clues about how galaxies and large-scale structures formed. Quasars also challenge our understanding of black hole physics. At their core lies a paradox: how can a black hole, which traps light, be surrounded by such brilliance? The answer lies in the extreme environment of the accretion disk. As matter spirals into the black hole, it is compressed and heated to such an extent that it emits energy more efficiently than any known process. This energy is radiated outward, escaping the gravitational pull of the black hole and traveling across the universe. The accretion process is so efficient that even a small amount of infalling matter can produce an enormous amount of light, making quasars the most luminous objects in existence. But not all the matter drawn toward a black hole is consumed. Some of it is ejected in the form of relativistic jets, narrow beams of plasma traveling at nearly the speed of light. These jets are among the most powerful phenomena in the universe, capable of extending for millions of light-years and influencing regions far beyond the host galaxy. They interact with intergalactic gas, heating it and creating shock waves that ripple across space. The mechanics of these jets remain one of the great mysteries of astrophysics, but they are believed to be powered by magnetic fields twisted by the rotation of the black hole and its accretion disk. As we observe quasars, we are not only studying the past but also exploring possibilities for the future. Advanced telescopes and instruments are unlocking hidden quasars, those obscured by thick clouds of gas and dust. These discoveries are painting a more complete picture of the universe's early days, revealing a time when quasars were far more common and likely played a crucial role in shaping the cosmos. The James Webb Space Telescope, with its infrared capabilities, is uncovering quasars from the universe's first billion years, providing unprecedented insights into how the first black holes and galaxies formed. The idea of harnessing the power of quasars also sparks the imagination. Could advanced civilizations, if they exist, tap into the energy of these cosmic powerhouses? The energy output of a single quasar dwarfs that of all the stars in a galaxy combined, enough to sustain a civilization for millions of years. Hypothetical megastructures, like Dyson spheres, have been proposed as a means of capturing this energy. While purely speculative, such ideas push the boundaries of what we can conceive and remind us of the universe's limitless possibilities. Quasars also evoke deep philosophical questions. They remind us of the vastness of time and space, of processes that began billions of years before we existed and will continue long after we are gone. They challenge us to think about our place in the cosmos, to reflect on the improbability of our existence in a universe so immense. And yet, despite their remoteness, quasars connect us to the farthest reaches of the universe. Their light, traveling across billions of years, is a bridge between the past and the present, between the known and the unknown. The study of quasars is a testament to human curiosity and ingenuity. From their discovery as mysterious radio sources to their recognition as cosmic beacons, quasars have driven technological and scientific advancements. Each observation, each discovery, brings us closer to understanding the universe's origins and its ultimate fate. And yet, as we learn more, new questions arise, ensuring that the quest for knowledge never ends. As you gaze into the night sky, consider the story of a quasar. Its light began its journey long before the Earth existed, crossing the vast expanse of the cosmos to reach you. It carries with it the history of a universe that has been evolving for billions of years, a universe that we are only beginning to understand. Quasars are not just lights in the darkness, they are the storytellers of the cosmos, guiding us toward a deeper understanding of the infinite. And in their light, we find inspiration, wonder, and the boundless potential of discovery. The story of quasars continues to unfold, each new discovery revealing layers of complexity and wonder. These cosmic titans, born in the turbulent hearts of galaxies, remind us that the universe is a dynamic, ever-changing place. Their light, though ancient, carries the essence of creation and destruction, painting a picture of a cosmos where forces beyond comprehension sculpt the structures we see today. Imagine standing at the edge of a galaxy billions of years ago, witnessing the ignition of a quasar. Gas and dust are drawn inexorably toward the central black hole, their journey marked by collisions, turbulence, and intense radiation. The quasar's light grows brighter, outshining every star in the galaxy. For millions of years, this cosmic beacon will dominate its environment, its power influencing not just the galaxy it inhabits but also the space around it. The energy output of quasars is almost unfathomable. In a single second, a quasar can emit more energy than our Sun will produce over its entire 10 billion-year lifetime. This energy is not just confined to light, it includes powerful jets of particles and winds that ripple across the universe. These emissions are so intense that they can heat the intergalactic medium, a vast expanse of gas and plasma that fills the space between galaxies. By heating this medium, quasars regulate the flow of matter, determining where stars and galaxies can form. But the power of quasars extends beyond their immediate surroundings. Their light, traveling across billions of light-years, interacts with the universe in ways that leave subtle but measurable imprints. For example, as quasar light passes through clouds of gas, it absorbs specific wavelengths, creating a unique spectral fingerprint. These absorption lines tell scientists about the composition, temperature, and density of the gas, offering a glimpse into conditions that existed billions of years ago. One of the most intriguing phenomena associated with quasars is gravitational lensing. When a quasar's light passes near a massive object like a galaxy cluster, the intense gravity of the cluster bends the light, creating multiple images of the quasar. These cosmic mirages not only magnify the quasar but also provide a unique opportunity to study the distribution of dark matter, the invisible substance that makes up most of the universe's mass. By analyzing the patterns of these lensing effects, scientists can map the otherwise hidden structures that shape the cosmos. Quasars also serve as cosmic chronometers, helping scientists measure the universe's expansion. As light from a quasar stretches during its journey to Earth, it shifts to longer, redder wavelengths, a phenomenon known as redshift. The degree of this redshift reveals how much the universe has expanded since the light was emitted. By studying quasars at different distances, astronomers can chart the history of cosmic expansion and gain insights into the mysterious force driving it, dark energy. This enigmatic force, which accounts for about 68% of the universe's total energy, is accelerating the expansion, pulling galaxies farther apart and shaping the universe's ultimate fate. While quasars reveal much about the past, they also challenge our understanding of how the universe functions. Consider the supermassive black holes at the centers of quasars. How did these monsters grow so large, so quickly, in the early universe? Some theories propose that they formed from the direct collapse of massive gas clouds, bypassing the slower process of star formation and stellar death. Others suggest that black holes grew through rapid accretion, consuming matter at rates that defy our current understanding. Each new discovery adds another piece to this cosmic puzzle, bringing us closer to understanding the origins of these enigmatic giants. The study of quasars has also pushed the boundaries of technology. Telescopes capable of detecting faint signals from distant quasars require precision engineering and cutting-edge materials. Instruments like the James Webb Space Telescope and the Square Kilometre Array are designed to peer deeper into the universe than ever before, uncovering quasars from the first billion years after the Big Bang. These observations will shed light on the earliest epochs of cosmic history, revealing how the first galaxies and black holes emerged from the primordial chaos. Quasars also inspire us to think about the possibility of advanced civilizations elsewhere in the universe. Could a civilization harness the power of a quasar, using its immense energy to fuel technological advancements or interstellar exploration? This idea, while speculative, reflects the awe-inspiring nature of quasars and their potential as sources of unlimited energy. The concept of a megastructure, like a Dyson sphere, surrounding a quasar and capturing its output challenges us to imagine what might be possible in a universe filled with wonders. Beyond their scientific and speculative significance, quasars evoke a profound sense of wonder. They remind us of the vastness of the cosmos, of processes that operate on scales of time and space far beyond our everyday experience. To observe a quasar is to connect with the universe's history, to witness a moment frozen in light that has traveled billions of years to reach us. It's a reminder that we are part of something much greater, a cosmos that is ancient, expansive, and filled with mysteries waiting to be uncovered. Quasars are not just objects to be studied, they are symbols of our curiosity and our desire to explore. They challenge us to ask big questions about the universe. Where did we come from? How does the universe work? What lies beyond what we can see? In their light, we find inspiration to look deeper, to push further, and to never stop seeking answers. As you contemplate the night sky, consider the journey of a single photon from a distant quasar. Born in the chaotic heart of a galaxy billions of years ago, it traveled across the cosmos, passing through intergalactic voids, bending around massive structures, and finally reaching Earth. That photon carries with it the story of its origin, a tale of creation, energy, and transformation. And as it reaches your eye, it connects you to the universe in a way that is both intimate and profound. Quasars, these beacons of light, are more than celestial objects, they are the storytellers of the cosmos. Through them, we glimpse the universe's grandeur, its complexity, and its beauty. They remind us that in the vast expanse of space, there is always more to discover, more to understand, and more to marvel at. In their light, we see the infinite possibilities of existence, and in studying them, we come closer to understanding the fabric of reality itself. The light of quasars continues to serve as a profound bridge between the infinite past and the boundless future. These celestial beacons, born from the fiery hearts of supermassive black holes, invite us to unravel their mysteries and marvel at the raw power they embody. Their radiance, visible across billions of light-years, holds the echoes of the universe's earliest chapters, a time when galaxies were just beginning to form, and the universe itself was still taking shape. Imagine standing on a planet within a young galaxy, watching as the central black hole devours matter from its surroundings, sparking the birth of a quasar. The sky is ablaze with its light, a constant reminder of the immense forces at work in the heart of the galaxy. Over millions of years, this quasar will reshape its environment, its radiation and jets influencing the formation of stars and the dynamics of the galaxy itself. Yet, the quasar's brilliance is temporary. When its fuel is exhausted, the light will fade, leaving behind a dormant black hole, a silent giant at the core of the galaxy. This life cycle of a quasar is a testament to the universe's impermanence and constant evolution. From their birth in chaotic collisions to their eventual dormancy, quasars remind us that even the most powerful phenomena are part of a larger cosmic dance. Galaxies merge, black holes grow, and quasars ignite, only to fade again as the cycle continues. The jets of quasars are among their most awe-inspiring features. Stretching across hundreds of thousands, and sometimes millions, of light-years, these relativistic jets are the ultimate demonstrations of cosmic power. Their speed, approaching that of light, and their ability to pierce through intergalactic space make them unparalleled phenomena. As they travel, these jets interact with gas and matter, creating shock waves that ripple through the cosmos. They inject energy into their surroundings, influencing the formation of stars and the behavior of galaxies millions of light-years away. Quasars are also deeply connected to the mysterious dark matter and dark energy that dominate the universe. Dark matter, invisible but omnipresent, shapes the large-scale structure of the cosmos, providing the gravitational scaffolding around which galaxies form. Quasars allow us to map this unseen substance through phenomena like gravitational lensing, where the light of a distant quasar is bent by the gravitational field of a massive object in its path. These cosmic distortions provide a unique window into the distribution of dark matter and its role in shaping the universe. Dark energy, the enigmatic force driving the accelerated expansion of the universe, is another frontier that quasars help us explore. By studying the distribution and redshifts of quasars, scientists can refine their understanding of how the universe has expanded over time and predict its ultimate fate. Will the cosmos continue to expand forever, or will it eventually contract in a big crunch? The light of quasars, spanning billions of years, provides critical data to answer these profound questions. As telescopes become more advanced, our ability to study quasars improves dramatically. The James Webb Space Telescope is already revealing quasars from the universe's first billion years, offering unprecedented insights into the formation of black holes and the galaxies that host them. Meanwhile, radio telescopes like the Square Kilometre Array will detect faint radio emissions from distant quasars, uncovering even more of these enigmatic objects and deepening our understanding of the early universe. But the power of quasars is not just scientific, it's deeply philosophical. Their light, traveling across unimaginable distances, connects us to the farthest reaches of the cosmos. It reminds us that the universe is ancient and vast, filled with forces and phenomena far beyond our comprehension. Yet, despite this vastness, we have the ability to observe, understand,